Welcome to the Magnetosphere seminar series. This is Marco Silveira speaking. Today, we are delighted to have Dr. Angeline Burrell as our speaker. She is a research scientist in the ionospheric physics and applications sections of the Space Science Division at the US Naval Research Lab. Prior to obtaining her PhD, she worked as a scientific programmer. She started using Python in 2012 and started contributing to the community projects in 2013 and began her efforts to organize and improve the visibility of the space physics Python community in 2016. Something that I agree with her in 100%. She thinks that most people don't leave enough inline comments on their code, although I also don't do that. And today she's going to talking to us about Python in space physics. So before we begin, I'd like to remind you that this presentation is being recorded. So please keep your microphone on mute and post your questions and comments in the chat box. I will read them at the end of this presentation. So please go ahead, Dr. Burrell.
Thank you for inviting me to speak today. Next slide. There we go. So today I'm going to be talking about Python, and I'm going to break it up into 3 parts. First, I'll talk a bit about Python in general, and then space physics, specifically magnetospheric physics in particular. I'll end by talking about responsible programming practices and present some resources for people to dive in more deeply. Next slide. So why is Python useful for our field? How can you get started? And how can you go beyond the initial hello world? This is where we're going to begin. Next. So one thing that's important to keep in mind, especially for the academics in attendance, is that most of the students we work with in the field will at one time or another take a job that's not in our field. This isn't a failure, this is a good thing. And with this in mind, it's imperative that we use research tools that are relevant to other disciplines and career paths. So the slide I'm showing here has a plot that gives the TOB programming community index. Python is in green, and you can see that as of August, when I made this slide, Python was the 3rd most popular language that's used in programming in general. So by using Python in your research with your students, you're giving them a transferable skill. The other 2 languages above it are C and Java, and they've been at the top for ages. So Python's doing really good. The other 2 languages that we use frequently in our field are MATLAB and IDL. And as you can see, those rank a lot further down in popularity, with MATLAB at 16th and IDL above 100 and below 50. All right, next slide. Another good thing about Python is that it's named after a flying circus, which means that it can help you fly, which is just fun. Next. So perhaps you aren't impressed by flying or transferable skills because you don't have students. This slide gives you a lot of reasons why you should be using Python for your research. When I started to use Python, I was at first using a mix of Perl, GNU-plot, and Igor, the last one thanks to my PhD advisor. And the things that won me over were the inclusion of tools I had used all the time and had to build, such as matrix calculations, basic statistical calculations, and file reading. Time handling was simple and easy. You didn't have to worry about year rollover or leap years. It wasn't hard to install, and the coding style was easy to adapt to. I consider myself fundamentally a C programmer, so the white space was initially a bit spooky, but you eventually get over that. So now that another good thing about Python is that the community is very invested in it, and it's established standards which are easy to search online. so that you can develop a style that if you use it, you can work with Python code that anyone has written, which makes community programs a lot easier to develop and continue. All right, next slide. Python is accessible on all the major operating systems. On Unix or Linux, it's already there, though you might not have the most recent version that you like. You can get that either from the source or from a distribution like Anaconda. On Macs, the situation is similar, but it comes with a special version of Python that doesn't behave the way that it should, so you should not use it, whether or not it's up to date. You should install it from a distribution like Anaconda or MacPorts or Homebrew, or get it from the source. Windows, I don't believe it comes with one, but again, Anaconda works there, and I believe there's a few others. I don't use Windows, so I can't give you as many advice there. Once you have Python, you can install as many or as few supporting modules as you like. Modules are program packages, such as the fictitious anti-grav that was in the Python is fun slide. The primary modules space scientists are going to use are numpy, numeric Python, SciPy, scientific Python, matplotlib, which gives you plotting using MATLAB as its base, and something like IPython, an interactive way of running Python in a terminal window. That's what I like. Other people use more integrated IDEs, but in any way, it lets you do analysis on the fly or work out your algorithm without needing to write a script initially. Next slide. So now that everyone here is 100% on board with Python, let's go through a simple example where we make a nicely formatted figure that shows a sine wave. If you like, you can follow along on your computer. I'm pretending that I'm using IPython here. I don't like IDEs, so that's what I use. Click, please. So to start, we need to import the necessary modules to give us the tools that we need to use with. You do that by typing import and then the module name. As is a useful way of making a long name that you need to type a lot shorter by giving it a nickname. So numpy is usually abbreviated to NP, matplotlib is MPL, and so on. Click again. You can plot things interactively in IPython using interactive on, the command shown here. It's great if you're messing around and you need to get a handle on a new data analysis method, but you can also turn it off using IOF when you're scripting things. Click. The first thing we need to do is open a figure, which we do using the pyplot submodule of matplotlib. Click again. Once we have a figure, we can add a plotting axis. There are a lot of things you can do to the figure, and if you type fig dot and then tab, you'll get a list of possible functions that will display in your window. For now though, let's go back to creating our sine wave. Next slide. So what we need to do first is get some data. Numpy lets us create an array with a specified interval that starts at a given minimum and ends before the given maximum using NP arange. This array can be made up of integers or floats, but it will only contain integers if all three of the inputs, the minimum, the maximum, and the interval in that order, are integers. So by having the last one, the interval be a float, everything is going to come out as a float. We don't need to do all the calculations before plotting. It's perfectly okay to do both at the same time. If you click, please. So here we have theta, our arange, as the x variable, and then we calculate the sine as the y variable. So here we're converting from the degrees that we put theta in into radians using the radians command. and then from that calculating sign using NP sign. Next, we specify the format, and we've decided to use a dashed line. And then we have some keyword arguments, where we specify the color and the width of the line. There are lots of different keyword arguments that you can use, and you can put the keyword arguments in any order so long as they're all specified by name and they come after the arguments, which don't need a name to be specified. All right. Python defaults to its own X and Y limits, but that's not necessarily what we want, so we can set them to be what we want. You can see that theta here has functions attached to it as well, min and max. So we can set our X limits using our theta array. We can then put the ticks at the location we want, something that's more sensible for degrees, and provide a nice, beautiful label. Those of you who use LaTeX will notice that Python uses the LaTeX notation. You often need the R in front so that things like /t, which can also mean tab, are interpreted in the LaTeX context instead of the line break or white space context. Then we add a grid and we add a title. And now we have a nicely labeled plot with the units specified over the desired range. And you could put that in a paper if for some reason you wanted to have a figure of a simple sine wave. All right, next slide. So now that we know the basics of Python, let's take a look at Python in space physics. There are many space physics packages, and we're going to take a closer look at those categories that I've shown here. So yeah, next slide, please. So the state of Pythonic space physics is healthy and vibrant. There are a lot of free and open source software packages available that address a variety of common needs. The figure on the right is from a 2018 paper I led and lists many of the free and open source packages used by the solar, magnetospheric, ionospheric, and atmospheric communities. On the right, I've listed several newer modules that may be of special interest to the magnetospheric community. In the following slides, I'm going to briefly present the packages most likely to be interesting to the magnetospheric community in more detail. Next. So Spacepie is one of the most mature space physics packages. It's a community package. Its maintenance has experienced ups and downs because of this, but its developers are responsive and the current version of the software is straightforward to install and use. It includes location and time routines, file handling, including NASA CDF reading and writing capabilities, model tools, and analysis and visualization tools. A link to a recent presentation by one of the SciPy developers is included on this slide, and I've broken down the major elements of the code on the right. I'd recommend checking out the recent presentation because it will be a whole 45-minute presentation on using SciPy or Spacepie. Next. One important aspect of doing research is getting data. Space physics data sources are diverse, and there are several different packages that focus just on this aspect of research. PySpeedas contains data loading, analysis, and plotting tools for 22 missions and was recently presented as part of this seminar series, so I won't go into it in too much detail. Madrigal Web provides routines for downloading data from the Madrigal database. It makes it simpler to create download scripts and is meant to be used as a tool to write your own scripts. The Geodata package provides a friendlier interface to Madrigal Web, along with some data visualization tools. The VRES client retrieves data such as the swarm dataset from the ESA VRES server. It uses pandas and Xarray, two packages that are built on NumPy and designed to handle time series data sets and data sets with with a lot of different dimensions. PyDarn.io is a new library for loading SuperDarn data. It works with PyDarn, the new super darn data visualization library. Now, it doesn't help you download the data. You still need to get your own account from either the British Antarctic Survey or from Super Darn Canada. But once you have the data, this Python routine will help you read the custom files. PySat is an interface for downloading, loading, cleaning, managing, processing, and analyzing space physics data set. Like the VRES client, it's built on top of pandas and Xarray. It's currently undergoing a series overhaul to make a version that's suitable for managing data in both research and operational environments. A lot of the data sets it focuses on are more ionospheric, but there's some planetary and magnetospheric data sets as well. HelioPy provides a set of tools that work with 1D in situ time series measurements of space plasmas and focuses on solar and magnetospheric observations. All right, let's move on to the next slide, where we have model data tools, because not everyone deals in observational data. The packages here focus on different aspects of model data that haven't already been covered by Spacepie. AmGeo and Shime are useful for providing high latitude ionospheric boundaries. AmGeo is a Python tool for Amy, a model of high latitude electromagnetics that assimilates superdarn and or supermag data. Shime uses ISR and electric field measurements, as well as superdarn data to provide localized mesoscale drivers. Both of these provide inputs that can be used in larger models of the ionosphere magnetosphere's boundary condition. Analyzator is a tool for analyzing Vlasiator output, a model that is used to study plasma processes such as reconnection, particle acceleration, and shocks. PyAmps provides an interface for the AMPS model, while Reis Aurora provides a wrapper for the Reis Sergienko-Ivanov excitation rates model. I apologize for my pronunciation. PyForecast Tools provides tools for model validation and forecast verification. It works with or without Spacepie and is used by PySat models. PySat models uses PySat to load and manage model data and has a growing suite of tools designed for data model validation. Next. One thing you can never have enough of are magnetic coordinate systems. Again, Spacepie has many of your standard coordinate transformation tools, but you may need something more particular. ApexPy, AACGM version 2, and Seganenko are Python wrappers for the coordinate systems that give them their names. OCBPy grids data relative to the open-closed field line boundary, and OOMBV calculates orthogonal magnetic basis vectors. Next. There are also several orbit and ephemeris tools, though a few of them are maintained on a legacy basis. JPLFM and PyFM both recommend using Skyfield, a pure Python package that supports tracking orbits in several different coordinate systems. SGP4 is a fairly focused ephemeris package that works faster if the C++ can be installed, but can also just function solely with the Python code. Spacepie is a slightly larger toolkit that contains a suite of tools for planning and interpreting level 1 satellite data by wrapping the NAIF-C SPICE toolkit. Next. Many space physics data sets are now stored in a standard file reader. Spacepie, CDF-lib, and PySat CDF all contain routines for reading NASA CDF files. H5Py is a tool for reading and writing HTF5 files, and NetCDF for Python reads and writes NetCDF files. PyLTR and SSJ Auroral Boundaries are two data analysis routines that didn't really fit in anywhere else. PyLTR is a learning to rank toolkit for data mining, and SSJ Auroral Boundaries identifies the poleward and equatorward auroral boundaries from the reprocessed DMSP SSJ electron precipitation data, which is really useful if you need those. Next, yes. So the last package I'm going to mention today is Resin. Resin is the reproducible software environment, is a tool designed to improve scientific reproducibility and collaboration. Resin creates a virtual environment that can be used to store all of the data analysis code and results for a particular project. This container can then be shared between collaborators or published online. The NGO team is working to make this virtual environment easy for space physics researchers to do their work in by including commonly used community Python packages. The packages that they currently support are listed on the right, with the ones in bold being ones that I've already mentioned in this talk. You can see a lot of them are there, and even if they aren't, you can import your own and include them as part of the Resin bucket. So this is a great tool, not only for keeping track of your own research, because you can keep individual projects in separate environments and go back to them as you need to, because heaven knows we're never just working on one thing at a time. You can also, when you're done, trim it down, clean it up, and share the analysis code and data in particular for a particular paper or project, give it its own DOI, and make future collaborations and reproducibility a lot easier for your research. Next. So now let's talk a bit about responsible programming practices, which includes best practices, attribution, and accessibility. Next. Best practices for programming include using or supporting a current version of the language. For Python, this is currently 3.8. A slightly harder practice to adhere to is style. The code on the right shows a perfectly acceptable bit of Python code written by someone who came to Python from C. Next. You can learn about Python standards by reading the Python Enhancement Proposal 8, or PEP 8, and PEP 257. The latter proposal describes docstring conventions. Docstrings are the comments included between quotation marks. They're typically included after the definition of a function or class, and when you're programming, it will pop up as a description of the routine when you enter the question mark to get your help. The standard for this that I'm using here is the numpy doc standard, which a lot of people use, and includes listing the input parameters, listing the elements that are returned, having a very short description at the top. So if you just are curious what this function does, you can get that right away and not have to read down to the bottom. You can also include references if you're using someone's algorithm, so that when you go back to write your paper and you're in the data analysis section and you're like, oh, I used this function, what was the paper that this function is using for their algorithm? You can easily reference that in the future. So docstrings are great. It can also help you, if you just write down what you intend to do at the beginning, keep that scope in mind for your function. So now you can see that the code has been made a bit more Pythonic. It includes more of the Python style documentation. It's using numpy to use the not a number. And it's using built-in functions like len, to determine the size of the array instead of requiring the user to supply that on the input. Now, if we go to the next slide, you can see that there's still more room for improvement. Originally, it was not using very descriptive variables. Descriptive variables can help you figure out what the code's doing without even having a docstring, should someone be very lazy and have bad programming practices. So now you can see that the input is data and that I'm calculating an average without even necessarily needing to read the doc string. If we go to the next slide, you can see the inline comments are never a bad idea. It makes the first initialization a bit easier to understand if you're not familiar with the routine. And then it explains why I'm doing what I'm doing underneath it. Next. Finally, it's important to avoid duplication. You don't need to write an average routine. numpy already has one. And it even has two. It has one if you're not worried about having filler values in your data array, and another one that will avoid including any not a number filler values if you have a sparse data set. So use the tools that are already available for you and don't waste your time going over and reinventing the wheel and writing something that people have already written. Especially since you can go to their doc strings and see which algorithm they're using. All right, next slide. So the last bit of best practices I'm going to mention is the need to provide documentation. Utilities like Sphinx can help you build up a user manual for a larger project by generating documentation in a variety of output formats that use restructured text files and the doc strings contained within the code itself. Websites like Read the Docs can host this documentation if you've published your code and want others to be able to use it without having to email you constantly. And even for your own project, if you're starting to build up, say, your own model or your own data analysis suite, starting to add documentation at the beginning is a lot easier than coming to code that is huge and trying to remember all of the important bits, because you know how it works at that point and you're not going to be confused. Someone else comes in and they won't even know where to start. But that's one reason that community projects can be really useful, because when someone new comes in, they'll ask a lot of questions that you can then include in your documentation, because you know that those questions are what everyone else is asking as well. All right, next slide. So a common argument against open source data and software is the danger of plagiarism. When dealing with Python packages, there are two aspects of attribution that should be considered: citations and collaborations. Citations deal with providing scientists credit for their products, whether they be data sets, software, or theories. And collaborations deal with the ethics of building on another person's work, which happens frequently as people enter and leave the field. Providing a DOI for software is a well-established practice now. The most popular packages even provide a bibtext entries for their preferred citation method, such as the one shown on the right here for SciPy. Journals like JGR and the Journal of Open Source Software are good venues for publishing the details of new space physics packages. However, you can assign a DOI to your code at a much earlier stage using a repository like Zenodo, which is great for things like software packages because it's built to accommodate versioning. You'll have a DOI for the entire package and project overall, and then every time you have a new version, you get a new DOI that's tagged to that version. So people can either choose to cite the overall DOI for the project or the specific version that they've used. A tarball of the code is then kept so that they can go back and retrieve whatever version was used in the analysis for the project and reproduce the results exactly. Next slide. Accessibility is, of course, also important. If no one can get to your code, then they can't use it. You can publish your analysis code on repositories like GitHub, GitLab, Bitbucket. All of these use Git for version control and provide project management tools. If you are not familiar with version control or Git, it initially, yes, is a little bit difficult, but it's an incredibly valuable tool. It's basically saving your code in a way where you can go back and see what you did and see where you may have introduced a bug. I cannot recommend version control highly enough, even if you are only programming alone. If you're programming with other people, it is vital because you need to know who's done what when and prevent different people who may be working on the same bit of the code from stepping on each other's feet. For more self-contained projects, the Resin container is a great option, or any other docking type container. Data repositories like Zenodo and Figshare are available to provide DOIs for these. The flowchart on the right goes down a lot of different conversation tracks I've had with people on, you know, oh, I don't know if I should make my code open or not. And, you know, if you're doing science and you're coding, then yes, you should. If you don't know how, you can use the resources in this presentation or my 2018 paper, which goes into this in a lot more detail to get you on the right track. Talk to your colleagues who have done it already. Most of us are more than happy to share the knowledge that we have on this to make our whole community more open. If you don't want people to steal your work, that's why we have these DOIs and citations. You should, in your own work as well, make sure that when in your data analysis section that you're going through and attributing the different algorithms and tools that you use so that we can build up this habit and people aren't worried about their work not being appreciated anymore. If you don't want people to see how badly you've programmed, you can program better, but also you should do it anyway because everyone gets better as they do things more and everyone has created bad code and it doesn't matter. And someone might actually find a bug for you and it might be important and then your research could be better in the future. Even people I work with who are very good programmers, when I've gone over their code, I've been able to find small indexing errors or something that, you know, initially everything was fine. And then you get like 6 years into the data set and everything's off by a day. And, you know, that's a problem. And they wouldn't have noticed it because they wrote the code and it's a really small typo, but someone else looks at it and they can see it. So even if you don't like the way you program at the moment, put it out there and then, you know, things will get better. If you don't want people to misuse your code, then provide clear documentation. You know, people are going to misuse things eventually. It happens with our scientific results. It's why we have peer review. If you document your code, you will make this much less likely to happen. The only real reason that you wouldn't be able to do that is because you have either you're working with something sensitive. And in that case, okay, yeah, you know, you don't want to step on the government's or the corporation's toes. All right, next slide. So finally, when you make your code accessible, you want to make sure that it's appropriately licensed. The reference I've included here, Morin et al. 2012, is a very good overview of the different licenses available, and I recommend giving it a read. The institution you work at will also play a role, so be sure to talk to your legal department if you have one. Finally, because none of us are building up code from elementary particles, it's important to do your due diligence. If you're wrapping someone else's code, reach out to them and make sure that the code is properly acknowledged so that their work is also cited appropriately. Make sure you're following copyright rules and licenses when building on top of other packages. For instance, if they're using a permissive license, such as MIT or BSD, then you can do anything you want basically with the code as long as you give them credit. If it's copyleft, though, then your project must as well be copyleft. You can't build something proprietary off of copyleft code. So be sure that you read the license of the package that you're working on and treat it with respect. And yeah, finally, when you want to contribute to someone else's code, which is great, make sure you read the contributing guidelines and follow them, and make sure that you use their style. A lot of times, even if you're using PEP 8, there's individual variations in the way that different projects do things. So pay attention to the way that they're programming and follow a similar style so that when someone goes through and reads the code later, they don't have a jarring transition. The same way that when you write a paper with other people, you want to have a cohesive voice throughout. All right, next slide. And now we're at the end. I have a list of resources here that include links to Python, links to the style guides that I've mentioned, an intro to Python tool, and then links to some of the projects I've mentioned. The last two, HelioPython and the CDAR link, include lists of packages that are of interest to the community. So I would recommend going and browsing there. And if you end up contributing something new to the community, to include it in the HelioPython, and if appropriate, the CDAR community pages as well. I know CDAR is ionospheric, but I've been linking the magnetospheric packages there too, because there are a lot of interactions between the magnetosphere and ionosphere. And I think it's useful to have both. All right. If there are any questions, I'm happy to answer them.
Okay. Thank you, Angeline. It was very interesting talk, very informative. We have a couple questions. I will read them one by one. So the first one is from Eric Lund. He wants to know that, does Python distinguish between floats and doubles as C and Fortran do?
It does, but it's adaptive. So if you don't need to define a variable up top, and you can change what a variable is without a lot of casting. But for instance, int division is done differently than float division. And so it treats ints and floats differently, the same way that ints and floats are treated in C, as long as you don't recast it.
Mm-hmm. Okay.
Oh, in addition, sorry, the numpy package lets you specify 8-bit ints, 64-bit floats, so that you can get the int, long int, float, and double type distinction that you would normally get in C. But you need the numpy package to do that.
Okay, okay, thank you. So next question is from Justin Lee. It's mainly your preference on not using one IDE, or are there technical considerations? Some have built-in in console that supports running IPython.
So could you repeat that?
Yes, sorry. It's mainly your preference or not using the one IDE, or are there technical considerations?
Right.
And
so that's definitely a preference thing. You should use whatever environment you find most comfortable. I find, because if, for instance, if one needs to SSH into a computer and doesn't have a lot of graphical control, you can still use IPython because it's basically a slightly more interactive command line. Whereas if you're using an IDE, you need more graphical support for what's going on. But that's just entirely preference based on the way my workflow goes. If you prefer IDEs, there's PyCharm and Spider and several more that work really smoothly. I have a student right now who's using Spider and he likes that a lot.
Okay, thank you. And next question is from Jay. What is the most straightforward way to read a column-oriented text file of numbers for plotting?
So I like numpy load text, but pandas also has a CSV reader. They're straightforward and simple, and you can read any basic text file that way.
Okay, and for curiosity also from Jay, why is py pronounced p in numpy and pi everywhere else?
I don't know, but yeah, I think it's just what ends up flowing off the tongue of English speakers the easiest, which one you tend to go with. When I was in the UK, people would often rename it to be numpty because it looks so close to that word. But it's not a numpty package at all. It's a very nice package that does smart things.
Okay. And next question from Raj. Is there any place where sort of like a wish list is published for collaborative efforts?
Not that I know of. However, on GitHub, there's a flag called Good First Project. Mm-hmm. So if you're starting out and you're on the fence about collaborating, then you can go and find a bit of a project you're interested in that the developers think is an easy way to dive in. However, if you go through the projects and find one that you're interested in, and just email the people in charge, that's a great way to establish contact. Also, if you're unsure once you've read the contributing guidelines that you're not quite sure about the best way to contribute, emailing them is great because then you can hash out what you need or what you envision doing and how they envision that working with the project before you put in a lot of work. So I have a few community projects that I support, and when people have done that, the process has gone very smoothly. And when people have contributed without discussion, it's not that it's not great, it's just that the pull request usually needs a bit of reworking. And I know that's frustrating when you've already done a lot of work.
Okay. So also from Raj, he says that we know that many of the large scale models are written in Fortran. So are there efforts to rewrite them or just write wrappers to assess them in Python?
Yeah, Python will never replace Fortran. It is always going to be slower. So anything huge needs to be written in Fortran or C, depending on how huge it is. And that's why we have the capability to wrap it. So with a lot of the bigger models, what you get is readers for the output so that the analysis can be done. And a few more of them do have wrappers for the execution as well. But yes, it's a wrapper. And that really is the best way to do it.
Okay. I have a question myself. it's like all those tools that you mentioned, they talk easy to each other because, like, for example, I use IDL since I started doing research, not that long, but. And sometimes I have like two different libraries and they don't talk to each other. Like I have to, unmark one for the other one to run. So they're like, duplicity of codes and.
Yeah. I've not found a huge issue using multiple packages. A lot of them are built off of the same foundation. A lot of the routines that load in data are loading it into pandas or Xarray. If it's a smaller data set, they'll usually use numpy arrays. So, and all of those data types talk to each other. So the fundamental bits of what you're working with in the different modules are the same. You often get small bits of duplication, like the NASA CDF readers are a good example of that, where it's been rather difficult to write a pure Python reader. So it took PyCDF a while to get going. And Spacepie is a huge package. And initially, I just needed it to read CDF files. And that's a lot of baggage to include just to read CDF files. But it's hard to extract that. So I can see why the developers don't want to do that. And that was one of the reasons that PySet CDF got written. But like, that's a wrapper, it's hard to maintain and keep on different systems. So we're hoping to move over to the pure Python package. But that's an example of duplication that was created because it's hard to use the first package that came along because it came along with a lot of baggage. But as creating the lists at CDAR and PyHC efforts, I think has done a lot to make the work that other people have done more visible. So you can scan through and be like, okay, the thing I want doesn't exist. Or search through GitHub and be like, okay, the thing I want, maybe it does exist, but it doesn't work anymore. And the person who wrote it isn't in the field anymore, and they're not answering their emails. So yeah, let me take on that bit and bring it up to date. But yes, for the most part, the different packages do work well with each other because they're built on the same foundations and the foundations communicate well.
Okay, good, thank you. And Natalia is asking for you comment about the new Julian language.
I'm not familiar with that.
Okay. So, okay. So thank you again for this very nice talk. And before we go, I'd like to inform that there won't be a seminar on the next Monday, 12. It's a federal holiday in the US. So we will resume again on October 19th when Dr. Jim Drake will talk about magnetic reconnection and the structure of the magnetopoles. Thank you all again and have a nice week. Thank you, Angeline.
Thank you. It's a pleasure to be here.